Hello everyone and welcome to this lecture. In the previous lecture we saw how IID samples are very nice and informative about the underlying statistics, and we were thinking about how to extract some information out of from the samples, and we'll make some more progress in that direction in this lecture. Okay, in particular we'll define empirical distribution, which is a distribution that one can easily compute from the samples. And we will also look at descriptive statistics. Descriptive statistics are like from the samples, you calculate mean and variance and various things from the samples, and what is their connection to the distribution. Okay, so these are the kind of questions we will ask and answer in this lecture. So let's get started. So first of all, let's get started with empirical distribution. So the empirical distribution has this definition. You have a set of IID samples. You will see this will be a recurring theme in what we do from now on. Every time we'll start with IID samples. So you have IID samples x1 to xn, okay, distributed with the distribution of a random variable x. Common distribution is the distribution of a random variable x. Okay. So here is a notation. This hash is usually a number, okay, number of xi that are equal to t. Okay, so this is a count you can make. Okay, so the sample is given to you. You simply count how many times t occurs in the samples. Okay, so that is the number of xi equals t, and then once you do that, you can find a distribution. Okay, so what is this distribution? This distribution is basically probability of observing t as an outcome in this distribution is this hash xi equals t, number of time t occurred divided by n. Okay, so this defines a PMF, right? The distribution with this PMF, the random variable with this PMF, and that distribution is called the empirical distribution. Okay, so let me give an example. I think that's probably clear, and the example will make it very amply clear. Okay, so here is a situation where you have 20 samples, and these are the samples given to you: 1, 1, 0, 1, 0, 0, 0, 1, 0, like that. Okay, what is the empirical distribution of this sample? You first observe that there are so the first step is when you want to compute the empirical distribution, you first want to compute the range, right? So let me just get started here. You first want to compute the range, right? What is the range of the random variable? In some sense, range or the set of values that this takes is 0 and 1, isn't it? It takes value 0, it takes value 1. Okay. So in the empirical distribution, you need p of 0 and p of 1. How many times did 0 occur? You can count. You have to now count 1, 2, 3, 4, 5, 6, 7, 8. So it's 8 out of 20. So probability of 0 is 8 out of 20. Okay. So maybe I shouldn't say range. Range is 0, 1. So this is the empirical distribution. And 1, you can see it's 20 minus 8, so that's 12 by 20. Okay. So the empirical distribution takes two values. There are two outcomes, 0 and 1. 0 happens with probability 8 by 20, 1 happens with probability 12 by 20. And that came from the samples, right? Somebody gives you these samples, you have this empirical distribution. Okay. So here is another set of samples where you have 7 zeros and 13 ones in 20. Okay. So here now the empirical distribution will become again 0 and 1, just 0 and 1 occurring in this samples, and 0 occurs with probability 7 by 20, 1 occurs with the probability 13 by 20. Okay. Here's another set of samples. Look at this set, 1, 2, 0, 3. Now there is 2, 3 and all happening. So now if you look at the range, it's going to be 0, 1, 2, 3, isn't it? That's going to be the range. Okay. And if you want to compute the empirical probabilities, okay, you have to simply count how many times 0 occurred. 1, 2, 3, 4, 5, 6, 6 by 20. How many times 1 occurred? Again 6 by 20. How many times 2 occurred? 5 by 20. How many times 3 occurred? 3 by 20. That's the empirical distribution. As simple as that. It's almost high school level calculations. Given a sequence of numbers, how many times a particular number appears in that sequence, divide by the total number of numbers, you get a distribution, and that distribution is called the empirical distribution. So from any sample, you can compute the empirical distribution. Is that okay? Hopefully this is clear. It's a simple enough process. Okay. So, a few observations. So, these are the things where people get a little confused. So, what is this empirical distribution? Okay, given a sampling, right, an instance of the sample, I can compute the empirical distribution. Okay, now as the instance changes, my empirical distribution also changes. So, the empirical distribution, so supposing I define the common distribution of x, right, just by the common distribution, the empirical distribution does not get defined. Okay. So, in fact, the empirical distribution is a random quantity. Okay. What do I mean by random? Supposing the IID samples are generated according to Bernoulli half process or Bernoulli P process, right? Okay. So, here is the example. So, this t that occurs and p of t can change from one sampling to another. Okay. So, if you take 20 Bernoulli P samples we saw before, even in the previous slide we saw that there are different cases in which the empirical distribution keeps changing even though the underlying distribution is the same. Okay. So, I am going to say supposing it is a Bernoulli P samples, P is some half or something. First time you sample, you will get 20 samples, right, 0, 1 something. Okay. That might come to some 8 by 20 and 12 by 20. The next time you sample, you will get a different number of zeros, different number of ones. So, the empirical distribution depends on the actual sample instance, not just the sampling distribution. Okay. Right. Keep that in mind. So, there is a distinction between these two, right. Empirical distribution depends on the actual instance of the sampling that you get and not only on the sampling distribution. So, this is a more complicated quantity. Okay. So, it is a random quantity. So, descriptive statistics are usually properties of the empirical distribution. Okay. So, the problem with the distribution is it's a confusing quantity to keep track of, right. You have to keep track of the values it takes, you have to keep track of the fractions with which it happened, lots of things, lots of moving parts. You have to look at it and it will change from sampling to sampling, some letter may come, some number may not come. So, it's all difficult to keep track of. So, instead of keeping track of the entire empirical distribution, maybe you want to keep track of some statistic of the empirical distribution. Okay. So, that is where this descriptive statistics come in. Okay. So, mean of the empirical distribution you could look at, variance of the empirical distribution you could look at, probability of a particular event occurring according to the empirical distribution you can look at. So, these are the various descriptive statistics we will look at. We will look how they are computed given the samples and how they are related to the underlying distribution. So, that is what we are going to do next. Okay. So, what one hopes is, okay, so from sampling to sampling, the empirical distribution changes, its descriptive statistics change, right. However, if you observe a large number of samples, you are hoping that the values that you get for the empirical distribution itself, its properties, its descriptive statistics sort of become close to the properties of the underlying sampling distribution, which was the distribution of that x that we said that comes from the samples, right. So, if this were to happen, that is a good thing, isn't it? So, you have a way of going from the samples in the computing the empirical distribution, computing the the descriptive statistics, and that in some way, if it is connected to the underlying distribution in a very clear theoretical way, that would be a good thing, and that is what we are going to hope to do. Okay. So, we will start first with one of the simplest statistics you can compute, and that is called the sample mean. Okay. So, here is the definition for the sample mean. It is the mean of the empirical distribution in some sense. If x1, x2, xn are IID samples with some common distribution, the sample mean, which is denoted x bar, okay, this is a notation for the sample mean, and I will call it x bar. X bar is basically x1 plus x2 plus xn, the whole thing divided by n, okay, the average of the samples, right, sample mean, sample average, that is what the definition is. Given a particular sampling small x1 to small xn, the sample mean will take a particular value. Okay. The sample mean is a random variable, the way I have defined it, capital X1 to capital Xn are random variables, they are the samples, right, the random samples, random variables. the sample mean itself is a random variable. X bar is a random variable. It's defined as a function of x1, x2, xn, x1 plus x2 plus xn divided by n. Okay, so it's a random variable. Okay. If you are given a particular instance of the sample, one particular sample is x1, xn, xn, then the sample mean will take a particular value. Okay. So quite often when we describe these things, it's difficult to keep track of the difference between the random variable, instance, particular value taken by it, etc. People will simply say sample mean, sample mean, sample mean. Okay, so mean or average value, they will just say that. And you should be conscious of this difference between the IID sampling model, sampling distribution, and what you got from the actual samples, instance of the samples, and you should know the connection between the two, what is connected, what is not connected, you should. Okay. So let's see a few examples. Here is a n equals 20 example. Here are a set of samples. A value taken by x bar in this case is 12 by 20. Here is the next case, another sampling. Value taken by x bar is 13 by 20. Here is another sampling, okay, 1, 2, 3 of some distribution. Sample mean is 25 by 20. If you calculate all of that and do it, you get 20. Okay. So depending on the particular sampling that you have, right, your sample mean changes from sampling to sampling. Okay. So remember, the sample mean usually refers to the distribution, and also this values taken by that distribution, right? So by that random variable. Every time you get a sample, you will get a sample mean. Okay. So remember that sampling, the sample mean itself is a random variable, and it takes different values for different set of samples. Right? It's all seems quite simple, but you'll see soon enough you will get confused between where the probability comes, what is the value. Sample average is just one value, so what am I talking about probabilities, right? All these kind of confusions will come. So you have to remember the difference between the model for the sample. I have an IID model for the samples. I have n samples. I am assuming there is an IID model with which these n samples have gotten generated. That's my model. Then I have data. When I have data, data is a particular instance of that model. I have only particular values. I'm not going to have capital X1, capital X2 as data. Right? I'll have 1, 2, 3, 5, 10, whatever. Those are the values. So your sample mean will be an actual value. There the sample mean is a random variable, right? A function of random x1 plus x2, some x bar. That's your random. That random variable took this value in this sampling. Okay, so that's what's going on, and this should be clear enough in your mind. Okay, so let's see some illustrations. Bernoulli 0.5 samples. I'm going to change n. So here in this case, x1 to xn is IID according to this distribution: 0 with half, 1 with half, right? So if n were to be 5, if you're looking at just 5 samples, here is one possibility: 0, 0, 1, 1, 1, and your sample mean will work out as 3 by 5. Here's another possibility: 1, 1, 1, 0, 1, sample mean will work out as 4 by 5. 0, 1, 1, 1, 0, sample mean will be 3 by 5. Just giving you different values, right? So you see how the sample mean takes different values when the samplings give you different samples actually, right? So the underlying distribution is always the same, but you get different samples and different sample means. This can happen. Now let's go to n equals 20. If you go to n equals 20, there you go. Long set of samples, long set of samples, and the sample mean changes: 12 by 20, 13 by 20, 13 by 20. Okay, so this is how the sample mean works. Sample mean is always, you add up all the samples, divide by the number of samples. The sample mean keeps changing from distribution to distribution. Now supposing I go to n equals 200, it's difficult to write down all the samples that I got. I did a few simulations of 200 samples of, IID 0, 1, half, Bernoulli half samples. In the first sampling, I got 95 by 100. Second sampling, I got 102 by 200. So third sampling, I got 98 by 200. So this is what will happen. Different times you sample, you will keep getting different sample means. N equals 1000. Look at that. Now it's becoming, okay, so there's a mistake here in the slides. It should be 495 by 1000. It's not 200. Sorry about that. I corrected the slides I give you. So it's 495 by 1000, 490 by 1000, 504 by 1000. Notice now that the variation in the number of the sample means is decreasing as we increase n, right? So initially it was 3 by 5, 4 by 5. The variation was like as much as 1 by 5, which is 0.2, right? So notice the variation here. It's 0.495, 0.49, 0.504. The variation has dropped below 0.01. Right? It's 0.02 or 0.01. Okay? So it's gone down 10 times when you went from 5 samples to 1000 samples. So the sample mean And what is 0.5? 0.5 you can see clearly is also x bar, right? So the mean, the distribution mean, the mean of this distribution, what is the mean of this distribution? Equals half. So you see, as you increase the number of samples, the sample mean seems to be going close to the distribution mean. Okay, so at least in this observation, in my simulation, it's working out, and that turns out to be an important fact. We'll write down this fact later on, but you can see clearly in the observation that that's working out. So now let's look at different types of samples. Here is a normal 0, 1 sample. Okay, so I have n samples, IID normal 0, 1. You remember the normal distribution? Normal distribution has a density. It's 1 by root 2 pi e power minus x squared by 2. So you can plot this density if you like. It will look something like this. This will be this density fx of x. So normal distribution tends to take values closer to 0, and then it can take higher values also. Okay, the variance is 1. Okay, and that means something in the probability and all that. So that's the shape. So here is some experiment that I did with n equals 5. I got these samples, and the sample mean ended up being minus 0.25. Next time I did, I got 5 samples, 0.17. Next time I did, I got 5 samples, again 0.11. You can see the variation is about, it can be as high as 0.14 or maybe even higher than that, 0.3 variation, right? So there's quite a bit of variation in the sample mean. I repeated it for n equals 20. Okay, I don't want to write down the samples for you. I will show you later on in a Colab notebook how to generate these samples and how to calculate the sample means. It's easy enough. So you see, I got 0.08 minus 0.24, 0.41. Yeah, still it's varying. Notice what happens when I go to 200. I'm getting minus 0.01, 0.11, 0.12. Multiple times I do it. You can see already it's shrinking. And if you go to n equals 1000, it really shrinks sharply. Okay, so you get 0.04, minus 0.04, minus 0.02. So once again, the distribution mean is 0. Okay, so the distribution mean is 0, and the sample mean appears to be getting close to the distribution mean as n increases. So these are experiments. I mean, quite often one can write an expression, but sometimes it's good to see some actual values that you generated and sort of check that this is actually happening. So I would encourage you to have this Colab notebook, which is like your playground, right? So somebody explains the statistical result, I present a statistical result, quickly do a generation of numbers. I'll also show you some Colab notebooks for doing this. Do a generation of numbers and check that it's actually true. I mean, multiple times you generate, you seem to be getting the same sort of observation. It's a nice little experimental thing to do. Okay. So here is a theorem. It's an important result, very important result. Expected value and variance of sample mean. Remember, the sample mean is a random variable, right? x1 to xn are IID samples, and if the common distribution of the samples has a finite mean mu and finite variance sigma squared. So I'm going to assume that's the case. Okay, so these IID samples that I generated come from a certain distribution, that is a common distribution, and that distribution has a finite mean mu and finite variance sigma squared. If it is a PMF, you know how to calculate the mean and the variance. If it's a PDF, you know how to calculate the mean and the variance. It's just expected value of x, expected value of x squared. Mean and variance are calculated from that. Okay. Now the sample mean x bar is a function of all these samples, x1, x2 to xn. Okay. So x bar also you can calculate the expected value and the variance. The expected value ends up being mu, and the variance ends up being sigma squared by n. Okay, I'm not going to go into detail on the proofs, but the proof is not very hard, right? So expected value of x bar, expectation is linear, so you get expected value of x1 plus expected value of x2 plus so on till expected value of xn divided by n. Okay, and what are each of these things? Each of these things are mu, right? So it's n times mu by n, and that's just mu. It's easy to see. Variance is a little bit more complicated. You'll have to do expected value of x bar squared. Okay, so that if you do, you will get expected value of x1 squared plus dot 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 expected value of xn squared, and then you will have all these cross terms, right? So 2 times expected value of x1 x2 plus dot 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 2 times expected value of x1 xn. right, or xn minus 1 x, okay, all the possibilities that occur, and divided by n squared, okay, all right. So this is expected value of x bar squared. So you will have some expression here. Remember, these are all independent, right? So you will have that working out, and then each of these things are identical. So you will have this being n times expected value of x squared plus this will be, how many such products will be there? It's n into n minus 1 by 2. So there's 2 and 2 will cancel. You will get n into n minus 1 expected value of x the whole squared. So that's just mu squared, okay, by n squared. What's expected value of x squared? That is sigma square plus mu squared, right? So you will have n times sigma squared plus n times mu squared plus n squared times mu squared minus n times mu squared divided by n squared. So these two will cancel. So you just get sigma squared by n plus mu squared, okay. So that's expected value of x bar squared. So variance of x bar is just expected value of x bar squared minus expected value of x bar whole squared. So the mu square and mu square will cancel, and you simply get sigma squared by n, okay. So it's just a quick derivation. The derivation is not so important, but the final understanding of what this result means is extremely, extremely important, okay. The expected value of the sample mean equals the distribution mean, the mean of the distribution. The variance of the sample mean equals the variance of the distribution divided by n, okay. There is a by n that ends up coming in the denominator, okay. So notice that scaling, it's very important. The one thing, the expected value is just mu, but the variance becomes sigma squared by n. It goes divided by n, okay. Keep that in mind, that's very important. Okay, once again, remember, sample mean is a random variable. It changes from sampling to sampling. Even though it changes from sampling to sampling, its expected value is going to be equal to the expected value of the original distribution used in the sampling, okay. The variance, though, actually decreases with n. It's sigma squared by n, okay. So keep that in mind. So this is a crucial difference that happens in the sample mean, okay. So all that I've written down. Remember, the distribution mean is actually a number, okay. So it's not random or anything. The sample mean is random, and the sample mean's expected value is equal to also the expected value of the underlying sampling distribution. That is the important result, okay. More crucial, very, very crucial, is this variance falling with n. It decreases with n, it decreases as 1 by n. So as n increases, what is going to happen to x bar as a random variable, okay. As n increases, irrespective of n, x bar has the mean being always the same, okay. So mean of x bar, so if you were to plot, so let's say this is mu, okay, there is some sigma squared, okay. So x bar for small n, if n is equal to very small, like 5 or 10 or something, it's only sigma squared by 5. As n increases, the spread of the distribution of x bar, okay. So if you were to keep, like, say, I don't know, if x bar were to be discrete, supposing you're doing PMF of x bar, okay. So for small n, it would maybe have, something around. So it may spread out like this, okay. So this may happen for small n. What will happen for large n? What will happen for large n? As n goes higher and higher and higher, it's going to be very, very close to just this, okay, very close to mu. Remember, when variance goes down to 0, the values taken by the random variable come very close to the expected value, right? It doesn't go too far away. That's variance controls the spread of the distribution, right? High variance means high spread. Low variance means very low spread around the mean, okay? So as n increases, the distribution itself comes closer and closer to the mean, and that's the picture that you have to have in mind. Okay, the actual distribution we don't know. It may have some PMF taking some value, but we know that the spread of the PMF is going to be really small. It goes down as sigma squared by n. Okay, so one statement you can make very nicely is, as n blows up, as n increases, the values taken by the sample mean, just the values taken by the sample mean, as the samplings change, will always be close to the distribution mean. It won't be too far from the distribution mean. That's what this means. Okay, the upshot of this result is, if n is becoming larger and larger and larger, the values itself, the values taken by the sample mean, will be close to the distribution mean, not just the average of the sample mean. Okay, so the actual values itself will be close because the spread is not very large. Okay, so we'll see some examples and illustrations hopefully soon enough. Okay, but before that, let's just finish off one more descriptive statistic, which is called the sample variance. Okay, so once again you have IID samples, and the sample variance, which I will denote as capital S squared. Okay, so this is just a slightly different notation, S squared. It's a random variable which is defined in this fashion. Okay, x1 minus x bar squared plus x2 minus x bar squared plus dot 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 xn minus x bar squared divided by n minus 1, and this x bar is the sample mean. Okay, so how do you calculate the sample variance? Okay, given a particular sampling x1 to xn, you first find small x bar, which is the sample mean. You add up all the xi's, divide by n, you'll get the sample mean. Okay, and then you take this x1 minus x bar squared plus xn minus x bar squared divided by n minus 1, you will get the sample variance. So these are calculations you have done before in your statistics 1 class, so you should see this. So this is the sample variance. Okay, so often this, the actual instance is also called sample variance. The random variable is also called sample variance, but you should remember the difference when people talk about these things. Okay, why have I used n minus 1 instead of n in the denominator? N is also used by many people. So n minus 1 is used because of the next result. You'll see the next result becomes very clean if I use n minus 1 here. So that's why I've used n minus 1. Okay, so here is the big theorem. The big theorem says the expected value of the sample variance is equal to the variance of the distribution. Okay, so supposing you have IID samples or from a distribution which has a finite variance sigma squared, the sample variance is a random variable, but its expected value is equal to the distribution variance. Okay, so we saw before that the sample mean had expected value equal to the distribution mean, but its variance was falling with number of samples. As number of samples increased, its variance kept on falling. It went down to 0, so the spread became very small. Now, the sample variance, on the other hand, is going to have an expected value sigma squared. What about variance of the sample variance? Okay, we are not doing that kind of analysis. One can show for most reasonable cases, if it has a finite, the distribution is not very crazy, it has many more moments, then the variance of the sample variance will also go to 0. So the sample variance, if you calculate the sample variance, you can expect it to be close to the original distribution variance. Okay, so these are results. The result is much more important than proof and all that, so I'm not doing proofs for this result. You can write it down. The proof is not too difficult. Okay, so here is the this is the same thing as before. So the variance of the sample values of the sample variance are going to be close to the actual variance of the distribution. Okay, so as n increases, one can expect that the individual samplings will give you a variance which is close to the variance of the distribution. Okay, so these two descriptive statistics that we saw the empirical distribution. We maybe commented that it could be a complicated object, but if you calculate the sample mean and sample variance, we are already getting some valuable information about the underlying distribution. Remember, we were talking about what did we start all this from the IID samples. We want to extract some information about the underlying distribution, right? That was our goal. Okay, here are two descriptive statistics which appear to be giving us good information about the underlying distribution. One was the sample mean, very easy to calculate, just add up all the sample values, divide by n. But as n increases, that is going to go close to the distribution mean. That's great to have. Next is the sample variance. What does that give you? As n increases, you just compute the variance of the values that you get, that you can expect to go close to the sample actual variance of the distribution, except remember that n and n minus 1, it's not too critical, but n minus 1 gives you maybe slightly better accuracy. Okay, so that's a good thing to have. So simple descriptive statistics. So this gives us promise, right? So there can be simple statistical procedures, easy to execute and compute, and you can get information that's valuable about the distribution. Okay, let's do illustrations. Okay, so here are illustrations. I'll show you a Colab notebook code for this so that you can also run it and play with it. Here is a Bernoulli half simulation that I did. I'm not showing you the actual values because there's just too many values to simulate. You know, the mean of Bernoulli half is 1/2 and variance is 0.25. So I calculated sample variance values for n equals 20, n equals 200, n equals 1000. You can see it comes very, very close. So if I show you the Colab notebook, you'll see how to do this yourself. So you can see as n increases, the actual variance comes very, very close to the sample variance. Okay. So if you look at normal 0, 1, again a similar simulation, mean is 0 and variance is 1. You can calculate the sample variance values for n equals 20, 200, 1000, etc. And you can see how as you go to 1000, the sample variance comes very close to 1, which is the actual variance. So these are, I mean, this is just to convince you that, you know, the result is not just some abstract result. If you actually do a simulation, you do get exactly what is suggested. So the final statistic that we're going to see is something called the sample proportion. Okay, so this is very important as well. It's a very interesting and simple descriptive statistic to calculate from the samples. Okay, sample proportion. Okay, so let's say you have x1, xn distributed as x, which is IID. So I mentioned IID. These are IID samples. IID samples from the distribution of x. Okay. Now I have an event A which I have defined using x. Okay. I could define it as x being greater than t, or I could define it as x being between a and b. Whatever I want to do with x, I do, and then I define my event A. Okay. So quite often I'm interested in something called the sample proportion, which is basically the proportion of xi, the fraction of xi for which A is true. Okay. So remember, x1, x2 to xn are distributed according to x. What do I mean by A being true? As in A has occurred, right? The event, the value of xi corresponds to A, as in it's inside the event A. A event is a subset of the values that x can take in some sense. So the xi actually, the occurrence of xi, the value taken by xi is inside A. That's what it means. That's the numerator. Out of these n values, you know, maybe that could be true for some fraction of them, and that fraction is S of A. Okay, so this is the sample proportion of an event A. Now once again, the sample proportion is a random variable. It will change from sampling to sampling. Hopefully I have an illustration for you. Here's the illustration. Okay, so you have a sample 0, 1, 1, 0. You can calculate the sample proportion of x equals 1, that is 3/5. Here is other samples, minus 0.2, 1.1, 0.3, minus 1.2, 0.7. You can calculate all these sample proportions. What's the proportion of values for which x is less than or equal to 0? S of x less than or equal to 0, that's 2/5, right? So 2 out of the 5 cases. X is between 0 and 1, that is 2 out of the 5 cases again. X is greater than 1, that is 1 out of the 5 cases. Do you see how I'm doing this? Okay, so given any event defined using the common distribution, I can find the sample proportion of that event quite easily from the sample. Just straightforward computation. Here's the big result. Okay, so this is a very important and interesting result once again that ties up a simple statistical procedure that we do from the samples, right? So that's the common theme. Hopefully you get that. You have IID samples, and I'm doing a very simple computation with the samples, be it the sample mean or the sample variance, or in this case the sample proportion of values which satisfy a particular event A. And then I have this wonderful result which connects the probability with which, or the distribution value to that simple statistical procedure. Okay, so here is the connection. Okay, so you have IID samples from a distribution A of x. A is an event defined using x, and P of A is the probability of A. Okay, P of A is the probability of A according to the distribution of X, right? So if X were to be between A and B, I will integrate the density of X over A to B, or if X is A and B, if it's the PMF, then I will add up all the values of the PMF inside that. So that's what I would do to compute P of A. The sample proportion S of A is a random variable. Its expected value and variance are given by these two expressions here. The expected value of the sample proportion equals the probability of A. The variance of the sample proportion is probability of A times 1 minus probability of A divided by N. Okay, so notice how this works out. It's actually proof is very simple. I mean, I can convert the samples into Bernoulli P of A samples just by the indicator random variable, right? Yi is 1 if A is true for the xi, and yi is 0, otherwise you have now a Bernoulli P of A sample. And P of A is the sample mean of y1 to yn. Okay, and S of A, I'm sorry, so this S of A, sorry, this is not P of A, this is S of A. S of A is just the sample mean of y1 to yn, and the sample mean we know converges to the actual mean, which is P of A, and the sample variance, the variance of expected value of the sample mean converges to the distribution mean, so you get P of A. Variance of the sample mean goes to variance of the original distribution divided by n. The variance of the original distribution is P of A into 1 minus P of A, and that divided by n. Okay, so this has got the Bernoulli P of A has mean equal to P of A and variance equal to P of A times 1 minus P of A, right? So once you have the sample mean, S of A becoming the sample mean of this is IID Bernoulli P of A, then you can apply the theorem that you already know for the sample mean. Its expected value is equal to P of A, its variance is the variance divided by n. Okay, so the sample proportion, which is again a simple statistic we can calculate from the IID samples, is connected to the distribution. The probability of A according to the distribution is connected directly to the expected value of the sample proportion. So as n increases, we expect S of A to be close to P of A. That's it. Okay, mean of S of A equals P of A, variance of S of A tends to 0. So this is the important story here. Once again, we saw 3 simple statistical procedures computing 3 descriptive statistics. One was the sample mean, the other was the sample variance, the third was the sample proportion. All 3 of them are connected to corresponding information about the distribution. One is the distribution mean, the other is the distribution variance, and third is the distribution probability of that event according to the distribution. Okay, once again we will close with an illustration. I have x1 to xn being normal 0, 1. I generate a different number of samples and try to find probability that x is less than or equal to minus 1. This comes from the distribution. Right, so it will be integral from minus infinity to minus 1 of the distribution, 1 by root 2 pi e power minus x squared by 2 dx. This equals roughly 0.159 something. Okay, so that came from the distribution. I did this numerical integration and I got 0.159. You know how to do this, right? We have seen how this value can be obtained. Okay, so I took n equals 20 samples and actually found the sample proportion values. Okay, so I did this 5 times. Okay, sample proportion values, 5 samplings. Okay, so once again 5 samplings here and 5 samplings. For each sampling I have computed the sample proportion. Okay, so I took 20 samples. First time I got 0.15 as the sample proportion of x less than or equal to minus 1. How did I do it? Out of the 20 values, how many values were less than or equal to minus 1? I divided that by 20, I got 0.15. Then you get 0.2, 0.15, 0.15, 0.15. For every time I did 20 samples, 20 samples, 20 samples, 20 samples, 20 samples, those are the values I got. Next I took 200 samples. Okay, and then again counted the number of samples which were less than or equal to minus 1. In the first sampling I got 0.170. Next one I got 0.14, 0.15, 0.15, 0.16. Okay. Next I took n equals 1000. Again, the values were very close to 0.16. Okay, 160, 18, 162, 135, 153. You see some variation here, but I guess that depends on how you do the sampling and all that. Here's another value, same thing repeated. From the distribution I got 0.683 as the probability of -1 to 1. And then as I do samples and increase them, I get the sample proportion value. Again, 5 samplings for each of these number of samples. And you see the actual sample proportion comes very close to the probability that I want to calculate. Okay, so hopefully these procedures are convincing to you. So once again, let's go back to the original question that we started these 2 lectures with. Where have we seen IID samples? We saw them in Bernoulli trials. Okay, I've listed out on the R here as well. We saw them on Bernoulli trials, and the Bernoulli trials sample mean tends to the distribution mean. So you have Bernoulli P samples, the distribution mean is P, and the sample mean is fraction of successes. So I know the fraction of successes is going to go close to P. In Monte Carlo simulations, the sample proportion tends to the actual probability. You remember that's what we did, right? NA by N. The sample proportion in Monte Carlo simulation tends to the actual probability. Same with the histograms. How did we do? The number of values in the bin divided by the samples, that's going to tend towards the probability of a random variable falling inside that bin. Okay, so hopefully this couple of lectures here have convinced you that from IID samples there are simple statistical procedures that give you information about the distribution, and you can analyze and prove results about those statistical procedures that show you that the statistical procedure results in an expression or an answer which is close to the distribution mean, which is close to the distribution variance, which is close to the probability of an event according to the distribution. So all 3 are very interesting results, and hopefully we'll take this and move on. Okay, so what we're going to do in the next few lectures is see a little bit more about these kind of results. Where do these kind of results, how to analyze these kind of results, what are the theoretical implications, etc. We'll see them in the next few lectures, and then we'll jump into more examples and see how this can be used. Thank you very much.